So that kind of leads into the coherent technology, and you may or may not be familiar with coherent technology. It's a technology that's used to do the line side optics we talked about. Errol will take us much deeper into that and explain that much better than I can. But this technology is typically being used a lot for the very long haul. This is where it came in about 10 years ago into the market and kind of revolutionized the long haul market. As the market is very large for the coherent, but as these problems in the data center, as the technology gets more optimized, we see this optimization for sort of the metro regions, and now we're seeing this optimization for what we're calling edge, which is in sort of this 100-kilometer use for these data center interconnect applications. And so you're seeing this trend that the market generally, this is showing the market for coherent. So the blue is the edge reaches, the gray is the long haul, and the orange being the metro. Obviously, the market itself is just up and to the right, as everything seems to be in optics these days. But you're seeing the mix changing, whereas down a few years ago, it was dominated by the long haul. Once you move out to 2022, you're seeing that the edge reaches are actually starting to become much more significant. And the yellow curve here is meant to be showing that, what is the percentage of edge versus the long haul, which was the traditional starting place of the coherent technology. And it's getting up to a third. So a third of all coherent technology is expected to ship in a few years' time is going to be focused on this, what was considered uninteresting 10 years ago for this technology. This is getting very, very closer, and it's actually getting into these data centers that we're talking about. And we'll talk later about it's actually penetrating in, and when we look beyond 400 gig, it's a very interesting situation. Okay, so that's kind of the market. That's all the kind of the moving pieces around the market, the pressures that the industry is under. Obviously, with the cloud folks, they're very much not willing to pay a penny more than they consider reasonable, and so that's putting a lot of pressure onto all the innovations. Before I go into the next section, is there any questions on that aspect, or am I just talking to the choir on that?
Did that sort of say that ZR was basically 120 and under? Like that's sort of the corresponding?
Yes. Yeah, so ZR is kind of, the OIF ZR spec is kind of the response to that. This is from Signal. They did their market analysis based on 120. I think most of the OIF ZR spec is really focusing on the 80 to 100. It's more, it's not a technology issue, it's more of a latency concern, really. Okay, so we covered the network, we covered the market architecture. Just briefly want to talk about the ASICs, because this is what actually drives the direction why certain choices are made. We're constantly trying to get the bandwidth of the ASICs up. So everything, we used to build our systems with multiple chips. Now we typically can get it down to a single chip, depending on the architecture of the box, but for like a fixed box. And the bandwidth of that chip itself has been just going up and to the right. This is essentially Moore's law driving this. And so we've had the 3.2 terabit chips here. We're getting into the 6.4 terabit, 12.8 terabit chips are available now. Everyone's trying to think about how to go do 25.6 terabit. This is all great. This is what Moore's law allows you to go do. We do have a problem, though, because we can't get that much bandwidth on and off the chip. And I'll talk about that. But what that means is the I/O or the SerDes, that has to speed up with it as well. And when the I/O of the chip speeds up, the optics has to speed up with it. And that's the kind of the relationship I wanted to talk about. So when we look at a chip package, we have a certain number of balls, BGA package. There's only a certain spacing that we can get it less than, or else we can't actually attach it to the board and get the signals out without them interfering with each other. So we have a sort of a pitch limitation here. And then we have a manufacturing limitation that we put that on our board and we reflow it with our contract manufacturer. And once it gets too big, that starts to warp. So it's just a physical manufacturing limitation that we can't make these chips too much bigger than they are today. And this sort of 70 millimeter chip package is kind of like getting above 70 is getting hard. And so when we're trying to figure out how to go from a 3.2 terabit to a 12.8 terabit to a 25.6 terabit to a 50 terabit chip, we have to have these SerDes speeding up as well. So, you know, a lot of 25 gig I/O, all of the 100 gig E technology out there is largely based on 25 gig I/O. We're seeing a lot of 50 gig I/O happening now, and we're starting to figure out how to do 100 gigabit I/O. And this isn't going to stop, but right now we're sort of in this transition here between 50 and 100. But from an optics point of view, this is what drives the technology that we need to put in place. It's very painful for us to not have the optics speed as fast or faster than the ASIC speed. And so these SerDes, these I/O that I talk about, this really informs everything we do in the optics industry. And these are the big steps that as an industry from physically building the equipment, these are the big steps we take, right? So for a long time, 10 gigabit per second was the SerDes that we used. And when I talk about SerDes, this could be the I/O that's on your ASIC. It could also be the laser, how fast the laser is modulating. And the relationship between those two things, 1-to-1 is good. Doesn't always have to be 1-to-1. I'll explain that. But once we have something like 10 gigabit per second, we can go do things with it. We can do 10 gig E just as a single lane. We can do 40 gig E, so 4 lanes of 10. We can do 100 gig E as 10 lanes of 10. And this is the way to think about it. But these steps from 10 to 25 to 50, 100, those are the big steps. Everything changes there. All the technology changes. All the PCB material changes. All the connectors change. All the modulators on the lasers and detectors. All these things change. And so these are big steps for us to make. Once we've made the step, then we start shooting down and to the right, because it's always cheaper to be down and to the right. So if you're talking about 100 gig optics, up here as an example, I could have a 10 by 10 electrical interface into the module. I can have 10 by 10 optical on my fiber, or I can get down to here and I can have 100 gig electrical coming to the module, and I can have a single lane of 100 gig optical. And so in theory, that's going to be a heck of a lot cheaper, but it's all about doing it at the right time, right? And this is actually where we're at right now. There's a lot of people working on this. But if 10 years ago we tried to work on this, this would be a science experiment, and no one would be able to build it, afford it, cool it, right? So it's all about figuring out how to get down and to the right as quickly and efficiently as we can without blowing stuff up as we go. But this SerDes reuse is probably the one critical thing that the ASIC industry is looking to go do.